This episode was made possible through the continuing support of the Thought Emporium and viewers just like you. Check out the links in the description for more fun with high voltage and engineering, and for other ways that you can get involved and help me make videos just like this one. Thanks for hanging out, and I really appreciate your time. Have fun! Hi there guys, and welcome back to the shop. I'm Chris Bowden, and I'm here today with my very good friend,
Paul Kidwell.
So, this is, normally we do like Tesla coil stuff and things like that. Today, it's a little bit larger scale.
Okay.
We're doing power plant stuff.
All right.
So I have the video series Authorized Personnel Only. This is the first time you've ever appeared in an episode of that. And we're going to talk about a thing that I've had a ridiculous amount of comments and questions on. In our power plant, because it's 130 years old, we have the oldest, most original synchronization setup ever. A pair of lights that fade in and out with sync. We have, now that's what they used 100 years ago. 50 years ago, they used a mechanical analog synchroscope, which we have, and it's older than me. And now modern ones use like an LED moving dot synchroscope, and those aren't nearly as cool. But very few people have seen the blinky light, and I've got a lot of people that have questions about the blinky light. So Paul helped me out today, and we built this whole arrangement because this is Paul's world. You want to do electronics, measurement, and stuff, we're there. So we've got an oscilloscope here. This is our Rigol Delta Sierra 1054. We've got two channels we're using, and the two different channels come from two different synchroscopes, or two different function generators.
Okay.
And we're generating sine waves because that's what we make in the power plant, and that makes this behave right. And what I'm going to do is synchronize our model power plant to our model utility grid, and this will make sense how the lights work. So the weird thing with the lights that trips people up is how they're wired, and it's very not intuitive. So the wires that feed the blinky lights come from each side. One leg of, so you've got a light bulb and you've got two wires. One leg goes to the mains. It goes to the national power grid. You plug it in the wall. Okay. It sounds fancy, like we're connecting to the national power grid. Yeah, you do that when you plug something in the wall. Okay, you're there. The other leg of the light connects to our generator, whatever specific generator we're bringing on at that moment. Some of our power plants have more than one. And because the electricity is a sine wave, when they're in phase, okay, when they're together, they're at zero relative to each other. Even though the voltage is going from 0 up to 120 and 0 and down 120, like that, okay, even though the voltage is changing, voltage is a measurement of difference between two things. Whenever you measure voltage, you're measuring the difference of electrical potential from one thing to another. Usually, it's from whatever you're sticking your probe on to ground, but not always. And this is one of those not always. We're measuring the voltage relative between the two different systems so that we have the mighty national power grid and our wheedly little generator. And if they work together, give me a sine wave. If they work together, the voltage is nothing. There's no resistance. But if they're out of phase, then the voltage is huge because there's a difference in energy. And that's what we're doing. So I'm going to show you this on a scope, and then hopefully it'll make more sense. Because we have a scope, we have signal generators, and we have blinking lights, so we're going to make it happen. The only thing here that isn't like reasonably accurate is the wheedles. We've got wheedles, and that's just because of LEDs, because we couldn't get little blinky lights that tiny that we could power off our signal generators without having to run to the store. And this is all built from just stuff we had laying around. And yes, before you comment, we tried it with Christmas tree lights. It didn't work.
Yeah.
So
Audio output.
yeah, this is all audio level stuff. So if you look at the scope, you'll notice, oh, we're not doing the frequency measurement. Oh yeah, there it is, there it is. So here's our frequency measurement. down here. And right now it says we're at 63.7 hertz. So what we have is up here, the top trace, that is our national power grid. The bottom trace is our turbine that is obviously not in sync. And usually we're at this point when we first spun up the turbine and we're trying to get things into sync, we tend to speed it up. We tend to spin the turbine up a little bit faster because it's easier to bring it down. So what I'm going to do is turning this knob over here is the same thing as adjusting the wicket gate. And I'm going to bring it down slow. Now you can see, and this is where the wheedles actually help. You can see that while we're out of sync, see when the wheedles do their little dance? That moment is when the potential difference between these two reference voltages is so high that it turns the lights on. So even if you're not looking at the lights, you can tell when the lights come on. When it does the wheedle, the lights are on. So the lights only come on when they're very out of phase with each other. So if I bring this down and we slow this down, we can see that the presentations slow down and the lights come on for longer. And this is exactly what we're doing when we're adjusting the wicket gates and slowing things down. Until we hit a point. So right there, if I turn the generator on at that point, it would be bad. It would make loud, expensive noises. But you can see that the lights are on, and I can adjust us back and forth, because when we're like this, it isn't that we're just out of sync. We're completely out of sync at a higher speed. When I get lower and we're almost the same speed, well, now we're at pretty much the same speed, but we're moving in and out of phase. And that phase is the relationship of the top humps to the bottom humps, like where they are along the axis. So right now we're pretty much in sync for speed, but we're out of phase. And right there, we're perfectly in phase. That's where we want to be. And this is when you flip the big switch and turn the power plant on and connect us to the grid. But at this moment, the lights are completely dark. And that's when you want to make the changeover. Now, we don't do it by the lights. We do it by the meter on the synchroscope because it's way more accurate. But it is absolutely 100% possible to synchronize the entire power plant in the event the synchroscope just eats it and all you have is a little light. So we could lose the scope. We could even lose one of the lights. That's why there's two. So that in case one burns out, you know. Because if it was just one light and it happened to burn out at just the wrong moment, well, if the light's out, you're in sync. And if the light's burned out and you're not in sync, you're gonna have a bad day. So this is what it looks like when we're out a hair. You can see this is just gliding in and out slowly.
You can use the phase adjust without...
Oh yeah, I could do the phase adjust without the speed adjust, but if I'm not dead on in speed, so like it's still gonna move. But that's a quick basic explanation of how the blinky lights work, what they're doing, and why. If you have any more questions on this, please let me know because we're happy to answer them. But that's your scientific scale model of an entire hydroelectric power plant here. And I'm gonna take this out of phase and out of sync and show you just what the light does. And that's it. That's what we got. You guys have fun. I'm Chris Bowden.
And I'm Paul Kidwell.
And as always, we'll see you next time. I'm gonna twiddle the knob. I'm twiddling the knob.
Whoop, whoop, whoop,
That is so
whoop,
cool.
whoop.